Imagine chatting with your own technical documents and instantly getting easy-to-understand answers using a cutting-edge LLM. In fact, this is one of the most popular use cases of LangChain, widely used in customer service chatbots. In this video, we will cover an end-to-end example of chat conversation using the awesome LangChain, Chroma, and OpenAI. Let's dive in. Here's a breakdown of each step leading up to the completion of the final chat. Check the description below for links to the Jupyter Notebook. First, we're going to set up a Python virtual environment and install several Python packages like LangChain, OpenAI, and so on. We're also going to use an OpenAI API key, so make sure to export it or include it in the .env file. We'll be using GPT 3.5 Turbo model as it is more than sufficient and a lot cheaper than GPT-4. At the time of this recording, it costs less than 1 cent to run examples in this workbook. Document loaders deal with the specifics of accessing and converting data from a variety of different formats and sources into a standard document object, which consists of content and its metadata. There are more than 80 document loaders available to use with both structured and unstructured data. In this example, we'll load a PDF. Large language models have a distinct limitation known as the context window. The context window of LLMs is the maximum number of tokens the model can take as input. For example, GPT 3.5 Turbo has a context window of 4,096 tokens, approximately corresponding to 3,500 words. To ensure everything fits within the context window, it's essential to break the document into smaller, more manageable pieces, allowing for some overlap between them. A chunk overlap is generally kept as a little overlap between two chunks, like a sliding window as we move from one to the other. This allows for the same piece of context to be at the end of one chunk and at the start of the other to help preserve context and to ensure semantic richness. The actual amount of overlap varies depending on the type of data and the specific use case, but something around 10 to 15% works for many scenarios. One of the most common types of text splitters in LangChain is the recursive character text splitter. The recursive character text splitter takes a large text and splits it based on the specified chunk size. It does this by using a set of characters. The default characters provided to it are the double new line, single new line, space, and then nothing, an empty string. First, it tries to split large text by the first character, double new line. If the first split by double new line is larger than chunk size, then it moves to the next character, which is single new line, and tries to split by it. If it is still larger, it moves to the next character in the set until we get a split that is less than our specified chunk size. Okay, let's do a quick test. Here is an example string to be split. Jack and Jill went up the hill to fetch a pail of water. Jack fell down and broke his crown, and Jill came tumbling after. In this example, first, we get two splits by the double new line character. These splits are larger than our 34-character chunk limit. So, we split by the new line character. We now get 4 splits. First 2 splits are good and the last split is also good, but the third split is still longer than 34 characters. So, we split it further using the space character, resulting in 2 smaller splits. This is how recursive character text splitter works. Notice that we do have a weird separation in the third and fourth splits. This is why we need a chunk overlap. We're going to utilize embeddings and vector stores to put these chunks into an index, whereby we can easily retrieve them when it comes time to answer questions about this data. So, you may ask, what exactly are these embeddings and vector stores and why we need them? First, embeddings. Embeddings take a piece of text, and they create a numerical representation of that text. Text with similar content will have similar vectors in this numeric space. What that means is that we can then compare those vectors and find pieces of text that are similar. We'll use OpenAI to create these embeddings. And now, vector store. A vector store is a database where you can easily look up similar vectors later on. This will be useful when we're trying to find documents that are relevant for a question at hand. We can then take the question at hand, create an embedding, and then do comparisons to all the different vectors in vector store, and then pick the n most similar. We then take those n most similar chunks, and pass them along with the question into an LLM to get back an answer. LangChain has integrations with well over 30 different vector stores. We're using Chroma because it's lightweight and in memory, which makes it very easy to get started with. We're going to want to save this vector store so that we can use it in future. So, let's create a variable called persist directory at doc/chroma. We're going to use the chat OpenAI model, GPT 3.5 Turbo, and we're going to set temperature equal to 0. This is really good when we want factual answers, because it has a low variability and usually gives us the most reliable answers with highest fidelity. Here we define a prompt template. It has two placeholders denoted by curly braces. One placeholder is for the context variable, this is where the retrieved documents will go. Another placeholder is for the question variable. And, this prompt template also has some instructions on how to use the context and question variables. We can now create a new retrieval QA chain. Question answering is done by the retrieval QA chain backed by a retrieval step. We can create it by passing in a language model, and then the vector database as a retriever. We're going to set the return source document to true. This will let us easily inspect the documents that we retrieve. Then we're also going to pass in a prompt that is the QA chain prompt we defined above. This is the easy part. We just need to invoke the LangChain QA chain we built with the query being equal to the question that we want to ask. And then, when we look at the result, we get the desired answer highly relevant to our PDF document. Okay, that's a wrap on today's episode. We hope you found it insightful and entertaining. If you did, please give us a thumbs up to let us know. Also, we love hearing from you, so please leave us a comment below. Share your thoughts, questions, or any topics you'd like us to cover in future videos.